Today in Lab 4, we try to create a sky image using a real dataset from LOFAR. Like previous weeks, we have an outline class here. You can download the code from this link shown here. In this class, we have the main function. This function, in the first step, reads an input file named viz and uv.txt. In this file, in fact, contains a data set of visibilities measured by the antennas in the LOFAR. Let me open this file. Okay, as we can see here, each line in this file consists of 4 complex visibilities, corresponding to 4 possible polarization of the radio wave received by the antennas in LOFAR. Here we have a wave vertically polarized. So as we can see here, the wave is polarized into 2 waves. These 2 waves, each with a specific amplitude and phase values. Anyway, please note that the details of signal processing are outside the scope of this module. I will explain later on how to use these polarized visibilities in the input file to build the target image. But please note that in LOFAR, the visibilities are polarized in terms of 2 3 values. Each in terms of 2 values. Each value represents the phase and amplitude of the polarized signal. So as I explained earlier, each visibility by LOFAR polarized into 4 signals. The amplitude and phase of each signal is shown as a pair like this. So here, the first value is the amplitude of the first polarization wave, and the next value is its amplitude. The second pair represents the amplitude and phase of the second polarized wave, and so on. First polarized wave, second, next, and last. At the end, we have 2 numbers. The last 2 numbers in each line represents the displacement values for any pair of antennas. If you remember here in this slide, we need the displacement value for each antenna. xp1 minus xp2 and yp1 minus yp2. So the last 2 numbers in each line represents the displacement values. So the first value is equal to xp1 minus xp2, and the final value shows the yp1 minus yp2 for any pair of antennas in loaf. The link to the file is here. So please download the file and use it as the input dataset. So in this dataset, we have visibilities and the displacement values for any pair of antennas in the LoFar. It could take some time because the file is a little big, around I think 100 megabytes. So it takes time to download the complete text file. Let's come back to the code. Here we have two matrices. The first one stores the output image created using the Fourier analysis. In other words, in the end, this matrix has a dirty image as discussed in the lecture. Another matrix named dirty beam holds the dirty beam that is mathematically extracted from the dirty image. Then we have a while loop. This while loop creates UV plane based on readings in the input dataset. So this while loop go through each line in the input text file to create UV plane, to create something like this, to find all points, all UV samples in the UV coverage. This while loop splits each line into separate fields. So in the input text file, we have 10 fields in each line. So as we can see in this while loop, the fields are extracted from each line. So the first 8 fields are amplitude and phase of polarization, polarized waves, and UV, as I mentioned earlier, are the displacement between two antennas in the LoFar. So all these fields are extracted from each line. Before going to the code, let's have a look at the inverse Fourier transform formula in slide 23. As shown here, we just need overall unpolarized visibilities. Here, everything is in terms of a complex number, not in polarized form. So we need to obtain the unpolarized visibility by adding XX and YY components of polarization. So here, as we can see, XX amplitude, XX phase, YY amplitude, and YY phases are used to convert the polarized wave into unpolarized visibility values. So here, as we can see, XX and YY components somehow, you know, processed to obtain the REVs and IMVs. Here in this slide, we mentioned that visibility is here is a complex number, real component and imaginary component. So here we create this real and imaginary part of the visibility. So anyway, you know, all these computations here first extract the fields from the file, from the input file, and then convert the polarized visibility to its equivalent in rectangular format. After that, the code divides U and V displacement values by the wavelength value. It is because, as discussed in slide 16, this U and V should be measured in unit of wavelengths. So here the displacement is divided by lambda, and the code performs the same. As we can see here, the x displacement and u and y displacement are divided by the wavelengths to find the u and v point. Okay, now we have the unparallelized visibility in terms of a complex number and UV point measured in the unit of wavelengths. So we are ready to build the image using the series discussed in slide 2023. Now we want to implement this sum. In this series, for each pixel L and M in the dirty image, we should calculate the inverse Fourier transform of visibilities in UV plane. So here in the inner loop, the inverse Fourier transform value for the unpolarized visibility is calculated, and the result is added to the pixel value in the dirty image. So as we can see here, this 2 pi I and blah, 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 blah is calculated. And then the visibility multiplied by this exponential term, and the result is stored in the raw image. So in each iteration of this for loop, we obtain a pixel value, a part of pixel value in raw image. We also calculate the dirty beam. So as we can see here, the result here, we accumulate the dirty beam values in this matrix. So anyway, In this for loop, we use the visibilities to obtain the raw image pixel values as we have the formula here, and the dirty bin. Okay. Please note that in this program, we also use the support class display density provided in lab 1. If you remember, in lab 1, we used a class named display density. Density. So please download this class from lab 1 and add it to your project. By the way, don't forget to set cell size to 4. So in the display density class, we have an integer number cell size. Please set the value of this cell size to 4. This way, the image, the displayed image will look bigger. So if you set the cell size to 4, the displayed raw dirty image will be bigger. Okay, after adding this imaging class and the display density class to your project, you can run the program to create the dirty image using the visibilities of antennas in the loafer. This program will run a bit slow, so please be patient. It takes time to go through all the lines in the input text file and process all the visibilities to create any pixel size, any pixel value in the dirty image. As the application, because you know here we add UV points to the UV plane, and we display the new UV plane once we add one new UV point. So in this while loop, UV point is calculated, and then it is added to the UV plane, and the plane is displayed. So as the application runs, we can see the UV coverage of entries read so far. You can see that the coverage is improving as more entries are added to the UV plane. So please just have a close eye on the UV coverage and see how the number of UV points increases as the application runs. In other words, as the Earth's rotating, more measurements have been recorded by the fixed antennas. So somehow you can see how we can increase the number of points in the UV plane as the Earth is rotating. So anyway, here we have the code, and I explained everything in this code, I think. So here we calculate the visibilities, UV points, and display UV plane once we add one new point to this UV plane. And here we calculate this sum to create the dirty image and also dirty B. Finally, at the end, finally in the end, the application displays dirty image and dirty B. This is the output. Okay, as I explained in the lecture, dirty images show, anyway, dirty images don't show a high quality sky image because, you know, here we create an approximation of the actual image, and this approximation doesn't have a high quality as actual image. You will recognize this once your program displays the output dirty image here. But to ensure we did everything right, I have loaded the same measurement set into KASA. KASA is a standard software package used by astronomers for imaging. So anyway, you can give visibilities or something like this input text file to this software application named KASA to create the output image or to create the dirty image of visibilities. I did this here. You can see the result. In fact, the output of this KASA application using this input text file. The output is something like this. If you compare your output, this dirty image, with this output get from KASA application, you can see that the outcome of our program here has the same structure with the output of this application. So it means that we did everything correct in this application. And we have implemented everything in the Imagine class in a correct way. Okay, now please start the coding phase, and please let me know if you have any question.